Tonight, we're going to take a journey that might permanently change how you see the ground beneath your feet. We're going to discover just how small Earth really is. Not in some vague, poetic sense, but in concrete, measurable terms that will leave you breathless. Because here's what most people never truly grasp. Earth isn't just small compared to the universe. Earth is so impossibly tiny that when you understand the true scale, you'll realize our planet is smaller than almost anything you can imagine, including the empty nothingness that fills most of existence. By the end of this journey, you won't just know that Earth is small. You'll feel it in your bones. Before we dive in, if you find these kinds of explorations fascinating, a quick like or subscribe would really help this channel grow. It's a small gesture, but it means everything. Now, let's begin. Let's start with something familiar. Earth, our home, the planet where every human being who has ever lived was born, lived out their entire existence, and died. From our perspective, standing on its surface, Earth seems enormous. You could spend your entire lifetime traveling and never see all of it. The continents stretch for thousands of miles. Mountain ranges take days to cross. Oceans seem to go on forever, horizon to horizon, nothing but water in every direction. For most of human history, Earth was everything. Ancient peoples believed it was the entire cosmos. The sky was just a dome overhead, perhaps with lights attached to it. The ground beneath was infinite, the center of all creation. This made perfect sense based on what they could observe. When you look out at the horizon, the Earth looks flat. It seems to go on forever. There's no indication from ground level that you're standing on a sphere, let alone a small one. The ancient Greeks thought the stars were fixed to a celestial sphere that rotated around us. The Babylonians believed Earth was a flat disk floating on an infinite sea. The Norse imagined Earth as a flat plain surrounded by ocean with a great serpent circling its edges. Every culture, in every time and place, looked at the world around them and concluded that they stood at the center of existence. And why wouldn't they? Everything they could see, everything they could touch, everything that mattered to their lives existed on this ground beneath their feet. Earth has a diameter of about 7,926 miles at the equator. That's the distance you'd travel if you could drill straight through the planet from one side to the other. If you started digging in New York City and somehow managed to dig in a perfectly straight line through the molten core, through the unimaginable heat and pressure at Earth's center, you'd emerge somewhere in the Indian Ocean, west of Australia. That's how far it is from one side of our planet to the other. If you wanted to walk around the equator, covering about 24,901 miles, and somehow you could walk on water, it would take you roughly 3 years at a steady pace of 20 miles per day. 3 years of walking every single day just to circle the planet once. That's a long journey by any human standard. Ferdinand Magellan's expedition, the first to circumnavigate the globe, took 3 years from 1519 to 1522, and most of the crew, including Magellan himself, didn't survive the journey. The Earth was so large that crossing it was a death-defying achievement. The surface area of Earth is approximately 197 million square miles. If you tried to visit every square mile of Earth's surface and spent just 1 second at each location, it would take you over 6 years of continuous movement, without sleeping, eating, or resting. 6 years of teleporting from place to place, spending just a single second at each location. That's how much surface area our planet has. Consider what that surface contains. Vast mountain, ranges like the Himalayas stretching for 1,500 miles across Asia, with peaks reaching nearly 30,000 feet into the sky. Deserts like the Sahara, covering 3.5 million square miles, an area larger than the entire continental United States. Ocean trenches plunging nearly 7 miles below the surface, deeper than Mount Everest is tall. Rainforests teeming with millions of species, many still undiscovered. Ice sheets covering Antarctica that are nearly 3 miles thick in places, containing 70% of all the fresh water on Earth. That's how big Earth is from a human perspective. It's genuinely large enough that no person could ever fully explore it in a lifetime. You could spend decades traveling and still find new places, new landscapes, new ecosystems you'd never seen before. Earth contains multitudes. But here's where our perspective begins to shift. The moment we compare Earth to anything else in space, our planet starts to shrink. Not physically, of course, but in significance. It stops being everything and becomes just one thing among many. And as we continue to zoom out, it gets smaller and smaller until it becomes something almost impossible to perceive. Our first comparison is the Moon, Earth's only natural satellite and our closest celestial neighbor. The Moon orbits Earth at an average distance of about 238,855 miles. That sounds far, and it is by human standards. If you could drive a car at highway speeds, say 60 miles per hour, directly to the Moon without stopping for gas or sleep, it would take you about 166 days. That's over 5 months of continuous driving just to reach the closest object to Earth in all of space. The Apollo astronauts, traveling at speeds of roughly 25,000 miles per hour, took about 3 days to make the journey. 3 days of hurtling through the void at speeds no human had ever experienced before, just to reach our nearest neighbor. When Neil Armstrong and Buzz Aldrin landed on the Moon in 1969, they had traveled farther from home than any human being in history. And yet, in cosmic terms, they had barely left the front porch. The Moon itself has a diameter of about 2,159 miles. That's roughly 27% of Earth's diameter. So the Moon is smaller than Earth, noticeably so. If Earth were a basketball, the Moon would be about the size of a tennis ball. That comparison might make Earth seem significant, and in this particular matchup, it is. The Moon is actually unusually large for a satellite. Most moons in our solar system are tiny compared to their parent planets. Mars has 2 moons, Phobos and Deimos, and both are just a few miles across, more like captured asteroids than proper moons. Jupiter has 79 known moons, but most are small rocky bodies that would fit inside a medium-sized city. Our Moon, by contrast, is a substantial world in its own right. It has mountains and valleys, craters and plains. It's large enough that its gravity affects Earth, causing the tides that rise and fall along our coastlines every day. But here's what's interesting about the Earth-Moon system. The distance between Earth and the Moon is about 30 times Earth's diameter. If you lined up 30 Earths in a row, they would just barely stretch from here to the Moon. Most people don't realize how much empty space exists between us and our closest neighbor. When you see illustrations of Earth and the Moon together, they're almost always shown much closer than they actually are, because the true scale would make the illustration impractical. If you drew Earth as a circle 1 inch in diameter, the Moon would need to be a 1/4 inch circle placed 30 inches away, 2.5 feet from the Earth. Most diagrams compress this distance dramatically giving us a false impression of how close the moon really is. This is our first hint about something profound. Space is mostly empty. Even in our immediate neighborhood, within the Earth-Moon system, there's vastly more nothing than something. The volume of space between Earth and the moon is enormous compared to the volumes of the objects themselves. If you could somehow scoop up all the empty space between Earth and the moon, it would dwarf both objects combined. And this pattern only becomes more extreme as we zoom out. Now let's move to the other planets in our solar system, and this is where Earth truly begins to look small. Mercury, the closest planet to the Sun, has a diameter of about 3,032 miles. That's roughly 38% of Earth's diameter. Mercury is genuinely small, and Earth is larger by comparison. If Earth were a grapefruit, Mercury would be a large marble. Mercury is so small that it's actually smaller than 2 moons in our solar system. Jupiter's moon, Ganymede, and Saturn's moon, Titan. A planet smaller than some moons. That's Mercury. So far, Earth is holding its own. Venus is often called Earth's twin because of similar size. It has a diameter of about 7,521 miles, roughly 95% of Earth's diameter. They're nearly the same size. Venus is actually closer to Earth in size than any other planet, which is part of why early astronomers thought it might harbour life. They imagined a planet like ours, perhaps covered in swamps and jungles, waiting to be explored. Of course, we now know Venus is a hellscape with surface temperatures hot enough to melt lead and an atmosphere of crushing carbon dioxide and sulfuric acid clouds. But in terms of size, Venus and Earth are practically siblings. Mars, the red planet, has a diameter of about 4,212 miles. That's only about 53% of Earth's diameter. Mars is significantly smaller than Earth. You could fit about 6.5 Mars-sized planets inside Earth's volume. Mars is small enough that its gravity is only 38% of Earth's. If you weigh 150 pounds on Earth, you weigh only 57 pounds on Mars. The red planet, for all its mystique, is a relatively small world. So among the rocky inner planets, Earth is actually the largest. It's bigger than Mercury, Venus, and Mars. If we only counted these 4 worlds, Earth would seem impressive. It's the biggest kid in this particular classroom, the king of the terrestrial planets, the largest rocky world in our solar system. But then we get the gas giants, and everything changes. Jupiter is a monster. It's the largest planet in our solar system by an enormous margin. Jupiter has a diameter of about 88,846 miles. That's roughly 11 times Earth's diameter. 11 Earths could fit side by side across Jupiter's face. But diameter only tells part of the story. Volume is where the comparison becomes staggering. Volume increases with the cube of diameter. This means that when something is 11 times wider, it's not 11 times bigger in volume. It's 11 times 11 times 11 times bigger. That's 1,331 times larger. Jupiter's volume is so immense that approximately 1,321 Earths could fit inside it. Let me say that again because it deserves emphasis. You could take Earth with all its continents and oceans, all its mountains and valleys, all its cities and wilderness, and duplicate it 1,321 times, and all those Earths would barely fill Jupiter's interior. Think about what that means. Every person who has ever lived, every civilization that has risen and fallen, every war fought, every love story, every triumph and tragedy of human history, all of it happened on a planet that's less than 1,000th of Jupiter's volume. Jupiter could hold all of human history multiplied by more than 1,000 with room to spare. Jupiter is so massive that it's almost a failed star. If it had been about 80 times more massive during its formation, the pressure and temperature at its core would have been enough to ignite nuclear fusion, and Jupiter would have become a small red dwarf star. Our solar system would have been a binary star system. Earth, if it existed at all, would orbit 2 suns instead of 1. Jupiter's famous Great Red Spot, a storm that has been raging for at least 350 years, is itself larger than Earth. A single storm on Jupiter is bigger than our entire planet. You could drop Earth into the Great Red Spot and it would disappear, swallowed by a hurricane that makes our worst typhoons look like gentle breezes. Saturn is nearly as impressive. With a diameter of about 72,367 miles, Saturn is slightly smaller than Jupiter, but still enormous compared to Earth. Saturn's volume could contain about 764 Earths, 764 copies of our planet, all crammed inside Saturn's pale yellow sphere. And Saturn has those magnificent rings that extend tens of thousands of miles from the planet's surface, making the total system even more vast. The rings themselves, though they look solid in pictures, are actually made of countless individual particles of ice and rock, ranging from tiny grains to chunks the size of houses. If you could spread Saturn's rings out flat, they'd cover an area larger than the distance from Earth to the Moon. And yet they're remarkably thin, averaging only about 30 feet from top to bottom. A cosmic compact disk, impossibly vast and impossibly thin. Uranus has a diameter of about 31,518 miles. That's still roughly 4 times Earth diameter. Uranus could hold about 63 Earths inside its volume, 63 copies of our planet, complete with all our continents and oceans, fitting inside a world most people barely think about. Neptune, the most distant planet from the Sun, has a diameter of about 30,599 miles. Neptune could contain about 57 Earths. Neptune is so far from the Sun that it takes 165 Earth years to complete a single orbit. If you were born on Neptune, you wouldn't celebrate your first birthday until you were 165 years old by Earth's calendar. Neptune has only completed 1 orbit around the Sun since it was discovered in 1846. Even Uranus and Neptune, the smaller of the gas giants, dwarf Earth completely. Our planet, which seemed so enormous when we started, is revealed to be a relatively small rocky world in a solar system dominated by gas giants. But we haven't reached the truly humbling comparison yet. We need to talk about the Sun. The Sun is a star. It's a massive ball of hydrogen and helium undergoing nuclear fusion in its core, releasing energy that keeps the entire solar system warm and lit. Every second, the Sun converts about 600 million tons of hydrogen into helium. This process releases an almost incomprehensible amount of energy. The Sun's total energy output is about 384 septillion watts. That's 384 followed by 24 zeros. In 1 second, the Sun produces more energy than humanity has used in all of recorded history. The Sun has a diameter of about 864,000 miles. That's 109 times Earth's diameter. You could line up 109 Earths across the face of the Sun and still not span its full width. If Earth were a peppercorn, the Sun would be a beach ball more than 8 inches in diameter. But again, volume is where the true scale becomes clear. The sun's volume is so immense that approximately 1,300,000 Earths could fit inside it. 1,300,000. That number is almost too large to comprehend. Imagine taking Earth and duplicating it 1,300,000 times. All those Earths, each one containing everything humanity has ever known. Every mountain range and ocean, every ecosystem and civilization, all of them packed together would just barely fill the sun. Let me try to make this more concrete. If you could somehow hollow out the sun and start dropping Earths into it, 1 per second, it would take you about 15 days of continuous dropping to fill it up. 15 days, dropping an entire Earth every single second to fill the volume of one star. And here's what makes this even more striking. The sun contains 99.86% of all the mass in the entire solar system. Everything else combined, all the planets, all the moons, all the asteroids and comets and dwarf planets, all of it together is only 0.14% of the solar system's total mass. Think about that. Jupiter, which seemed so massive just moments ago, the giant that could contain over 1,000 Earths, represents less than 0.1% of the solar system's mass. Saturn, Uranus, Neptune, all the gas giants combined, still amount to almost nothing compared to the sun. Earth is a tiny fraction of that tiny fraction. Our planet's mass is approximately 1/300,000th of the sun's mass. We're not just small, we're almost inconsequential in terms of the matter that makes up our solar system. The sun is so massive that its gravity dominates everything within trillions of miles. Every planet, every asteroid, every comet that wanders through our solar system, all of them dance to the sun's gravitational tune. Even the most distant objects in the Oort cloud, nearly 2 light years away, are still bound to the sun by gravity. The sun's influence extends for trillions of miles in every direction. But here's something even more mind-bending. The solar system itself is mostly empty space. The sun, massive as it is, sits at the center of an enormous volume of nearly nothing. Mercury, the closest planet, orbits at an average distance of about 36 million miles from the sun. Earth orbits at about 93 million miles. Neptune, the outermost major planet, orbits at an average distance of about 2,800,000,000 miles from the sun. If you drew a sphere around the sun that extended to Neptune's orbit, that sphere would have a radius of about 2,800,000,000 miles. The volume of that sphere is almost incomprehensibly vast, and within that volume, almost everything is empty space. Let me try to make this concrete. If you shrunk the sun down to the size of a basketball, about 9.5 inches in diameter, do you know how far away Earth would be? Earth would be a tiny speck, smaller than a pinhead, sitting about 86 feet away. That's the length of a basketball court. The basketball sun would be at one baseline, and tiny Earth would be near the opposite free throw line. Neptune, in this model, would be almost half a mile from the basketball sun. You'd need to walk for several minutes just to reach the outermost planet. And during that entire walk, you'd pass almost nothing. Just empty space with occasional tiny specks representing planets you'd likely miss entirely if you weren't looking carefully. And between all those planets, nothing. Empty space. Vacuum. The solar system is like a vast dark ocean with a few tiny islands scattered throughout. The sun, for all its mass, is still just a basketball in a space that extends for half a mile in every direction. Earth, in this scale model, would be a grain of sand sitting 86 feet from a basketball. That's how small we are just within our own solar system. The distances are staggering. The distance from Earth to Mars at their closest approach is about 34 million miles. That's close by cosmic standards, but it's still far enough that light takes over 3 minutes to travel between them. A radio signal from a Mars rover takes between 3 and 22 minutes to reach Earth, depending on where Mars is in its orbit. When NASA commands a rover to do something, they have to wait up to 44 minutes for a round-trip confirmation that the command was received. The distance from Earth to Jupiter at its closest is about 365 million miles. That's almost 10 times farther than Mars at its closest. When the Voyager 1 spacecraft was launched in 1977, it took nearly 2 years to reach Jupiter, traveling at speeds exceeding 35,000 miles per hour. Nearly 2 years of constant travel at speeds that would cross the United States in about 5 minutes, just to reach the fifth planet. The distance from Earth to Saturn is about 746 million miles at closest approach. To Neptune, it's about 2,700,000,000 miles. These distances are so vast that even light, traveling at 186,000 miles per second, takes hours to cross them. Light from the Sun takes over 4 hours to reach Neptune. And between all these planets, almost nothing. A few asteroids scattered through the asteroid belt between Mars and Jupiter. A few comets with their long elliptical orbits. The occasional spacecraft we've launched. But overwhelmingly, vacuum. Empty space. Nothingness. If you could somehow gather up all the matter in the solar system, all the planets and moons and asteroids and comets, everything except the Sun, and compress it into a single ball, that ball would be remarkably small compared to the volume of the solar system. Most of our solar system is empty space. The matter is just scattered islands in an ocean of vacuum. This is the first profound truth about Earth's smallness. We're not just small compared to other objects. We're small compared to the nothing that surrounds us. The empty spaces in our solar system are vastly larger than all the matter within it. Earth occupies an almost infinitesimally small portion of the solar system's volume. If the solar system out to Neptune's orbit were shrunk to the size of a football field, Earth would be a speck of dust somewhere near the 20-yard line. The Sun would be a marble at one end zone. And the rest of the field? Empty. Absolutely empty. Just grass and air representing the vacuum of space. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies left over from the solar system's formation. Pluto lives here, along with thousands of other dwarf planets and trans-Neptunian objects. The Kuiper Belt extends from Neptune's orbit outward for billions of miles. It's a ring of frozen debris, remnants from the solar system's violent birth 4.5 billion years ago. And beyond the Kuiper Belt is the Oort cloud, a theoretical spherical shell of icy objects that may extend up to 2 light-years from the Sun. That's almost halfway to the nearest star. The Oort cloud, if it exists as theorized, represents the true outer boundary of the Sun's gravitational influence. It contains perhaps trillions of icy objects, comets waiting to be disturbed by passing stars and sent tumbling toward the inner solar system. And Earth? Earth sits snugly in the inner solar system, 93 million miles from the Sun, completely invisible from these outer reaches. From the Oort cloud, the Sun itself would appear as just another bright star in the sky, perhaps the brightest, but still just a point of light. Earth would be utterly impossible to detect, lost in the glare of our star, too tiny and too close to the sun to be seen. We've come this far, and already Earth seems almost insignificant. We've compared it to planets that dwarf it, to a sun that could contain more than 1 million Earths, to a solar system that is overwhelmingly empty space. But we haven't even left our own stellar neighborhood yet. The solar system, for all its vastness, is just one star's domain. And there are hundreds of billions of stars in our galaxy alone. When we ventured out to the nearest stars and begin to comprehend the true scale of our galaxy, Earth doesn't just seem small, it effectively disappears. Our solar system, vast as it seems from Earth's perspective, is just one tiny island in an incomprehensibly large ocean. To understand Earth's true smallness, we need to journey beyond the sun's influence entirely and venture into interstellar space. We've already established that Earth is dwarfed by the gas giants, humbled by the sun, and lost in the emptiness of our solar system. But everything we've discussed so far, every planet, every moon, every asteroid and comet, all of it exists within the sun's gravitational embrace. We haven't even left home yet. We've been wandering around our own backyard, marveling at how big the yard seems, without ever stepping out onto the street. Now we're going to step out onto the street, and what we're going to find is that our entire solar system, everything we've discussed, is smaller than a single grain of sand on an infinite beach. The nearest star system to our sun is Alpha Centauri, a triple star system located about 4.37 light-years away. Now, that number might not mean much until you understand what a light-year actually represents. A light-year sounds like it might be a measure of time, but it's actually a measure of distance. It is the distance that light travels in 1 year. Light travels at approximately 186,000 miles per second. Let that sink in. 186,000 miles every single second. That's fast enough to circle Earth's equator about 7.5 times in 1 second. You could go from New York to Los Angeles in about 1/70th of a second. You could travel from Earth to the moon in about 1.3 seconds. Light is the fastest thing in the universe, the cosmic speed limit that nothing can exceed. In 1 year, light travels approximately 5,880,000,000,000 miles. That's a 5 followed by 12 zeros. 5 trillion miles. That's the distance of 1 light year. Alpha Centauri is 4.37 light years away. That means light from Alpha Centauri takes over 4 years to reach Earth. When you look at Alpha Centauri in the night sky, you're not seeing it as it is now. You're seeing it as it was more than 4 years ago. The light that enters your eye tonight left that star system back when you were 4 years younger. If something dramatic happened to Alpha Centauri right now, if one of its stars exploded or changed color, we wouldn't know for over 4 years. We'd keep seeing the old Alpha Centauri, unchanged and peaceful, while the actual star system had already transformed. In miles, the distance to Alpha Centauri is approximately 25,800,000,000,000 miles. That number is so large it's essentially meaningless to the human mind. We didn't evolve to comprehend distances like this. Our ancestors needed to judge whether a predator was close enough to be dangerous, or whether a fruit tree was worth walking to. Nothing in our evolutionary history prepared us for 25 trillion miles. Let me try to make that number meaningful. If you could somehow travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reaches speeds of about 430,000 miles per hour when it's closest to the sun, it would take you approximately 6,800 years to reach Alpha Centauri. 6,800 years. That's longer than all of recorded human history. The earliest writing systems appeared around 5,000 years ago in Mesopotamia. The Great Pyramid of Giza was built about 4,500 years ago. You would need to travel for longer than the entire span of written civilization, longer than the time from the first pharaohs to today, just to reach the nearest star. Voyager 1, the most distant human-made object, is currently about 15 billion miles from Earth. It was launched in 1977, nearly 50 years ago, and it's been traveling away from Earth ever since, moving at about 38,000 miles per hour. 15 billion miles sounds impressive, and it is. Voyager 1 has traveled farther from Earth than any human-made object in history. It's in interstellar space now, beyond the sun's magnetic influence. But here's the humbling truth. At its current speed, Voyager 1 would take approximately 70,000 years to reach Alpha Centauri if it were heading in that direction, which it's not. 70,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. 70,000 years ago, our ancestors were just beginning to spread out of Africa. They hadn't reached Europe or Asia yet. They hadn't painted the caves of Lascaux, or built Stonehenge, or invented writing, or agriculture, or cities. If they had launched Voyager 1 back then, it would just now be arriving at the nearest star. These distances are almost impossible to visualize. But let me try a different approach. Imagine shrinking our entire solar system, everything from the Sun to Neptune's orbit, down to the size of a quarter. At that scale, how far away would Alpha Centauri be? About 2 football fields away. 200 yards of absolutely nothing between your quarter-sized solar system and the nearest star. Now, imagine trying to find Earth on that quarter. You can't. Earth would be far smaller than the smallest speck visible to the human eye. It would take an electron microscope to even detect it. And that's just locating Earth within our own solar system before we've even crossed those 2 football fields of emptiness to reach the nearest star. Think about that. In a scale model where the solar system fits on a coin, the nearest star is 200 yards away. The gap between our solar system and the nearest star is thousands of times larger than the solar system itself. And here's the truly sobering part. Alpha Centauri is the nearest star system. It's our next door neighbor in cosmic terms. Most stars are much, much farther away. Sirius, the brightest star in our night sky, is about 8.6 light years away. That's roughly twice the distance to Alpha Centauri. The light you see from Sirius tonight left that star about 8.5 years ago. In our quarter-scale model, Sirius would be about 4 football fields away. Vega, another bright star visible in the summer sky, is about 25 light years away. That's almost 6 times the distance to Alpha Centauri. The light from Vega that you see tonight left that star around the year 2000, when many of you were children or not yet born. Polaris, the North Star that has guided travelers for millennia, is about 430 light years away. The light you see from Polaris tonight left that star around the year 1595, when Shakespeare was writing Romeo and Juliet and Queen Elizabeth I ruled England. Betelgeuse, the red giant that marks Orion's shoulder, is approximately 700 light years away. The light you see from Betelgeuse tonight left that star around the year 1325, during the height of the medieval period in Europe. The 100 Years' War between England and France hadn't started yet. The Black Death hadn't swept across Europe. Dante Alighieri had just finished writing the Divine Comedy. That's how long that light has been traveling toward your eyes. At these distances, Earth has completely vanished. It's not just small, it's undetectable, it's invisible, it might as well not exist. Let me paint you a picture to illustrate this. Imagine you're an astronomer living on a planet orbiting Alpha Centauri, the closest star to our Sun. You have advanced telescopes, far more powerful than anything we've built on Earth. You're looking back at our solar system. What would you see? You'd see the Sun as a bright star, similar in brightness to how Alpha Centauri appears from Earth. It would be one star among thousands visible in your sky. Nothing special, nothing remarkable. Just another yellow point of light in the darkness. With very precise instruments, you might detect a slight wobble in the Sun's position. This is how we detect many exoplanets from Earth, by measuring the tiny gravitational tug that planets exert on their host stars. The Sun wobbles slightly because Jupiter pulls on it. That wobble might be detectable from Alpha Centauri with sufficiently advanced technology. With even more sophisticated instruments, you might be able to detect Jupiter directly, perhaps by measuring how it blocks a tiny fraction of the Sun's light as it passes in front of the star. Jupiter is large enough and far enough from the Sun that it might be detectable from 4 light years away. But Earth? Absolutely not. Earth is far too small and far too close to the Sun to be detected. Our planet is lost in the Sun's glare, drowned out by the overwhelming brightness of our star. From Alpha Centauri, Earth would be completely invisible, undetectable, as if it doesn't exist. And Alpha Centauri is the closest star. From more distant stars, our Sun itself becomes just another point of light, indistinguishable from the thousands of other stars in that region of sky. You couldn't pick out our Sun from the crowd, let alone detect the tiny grain of rock orbiting it. Earth is so far below the threshold of detectability that it might as well not exist. All of human history, everything we've ever done, everyone who has ever lived, the entire story of life on our planet, all of it is happening on a world that's invisible from the nearest star. Let's zoom out even further. All these stars we've been discussing, our Sun, Alpha Centauri, Sirius, Vega, Polaris, Betelgeuse, and every single star you can see with your naked eye on the clearest, darkest night, they're all part of one structure, the Milky Way galaxy. The Milky Way is our home galaxy, a vast spiral of stars, gas, dust, and dark matter spinning slowly through the cosmos. When you go out on a truly dark night, far from city lights, and look up at the sky, you can see a pale band of light stretching from horizon to horizon. That milky smear across the darkness is our galaxy seen from inside. You're looking at the combined glow of hundreds of billions of stars, so distant and so numerous that they blur together into a continuous river of light. Every star you can see with your naked eye is part of the Milky Way. Every constellation, every asterism, every point of light that ancient peoples named and told stories about, all of them are our galactic neighbors. The night sky that has inspired poets and navigators and dreamers throughout human history is just a tiny, visible fraction of our cosmic home. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is difficult to determine because we're inside the galaxy, like trying to count all the trees in a forest while standing in the middle of it. Most estimates suggest around 200 to 300 billion stars. Let me try to make that number meaningful. If each star in the Milky Way were a grain of sand, you'd have enough sand to fill several large dump trucks. Our sun would be one grain in that pile, indistinguishable from all the others. You could search through that pile for years and never find our particular grain, never identify the one star among hundreds of billions where humanity lives. If you counted one star per second, 24 hours a day, 7 days a week without stopping to eat or sleep, it would take you about 6,300 years to count to 200 billion. That's longer than recorded human history. You'd start counting before the pyramids were built and still be counting today. The Milky Way is approximately 100,000 light years across. That's the distance light, traveling at 186,000 miles per second, covers in 100,000 years. In miles, the Milky Way is roughly 588 quadrillion miles from one edge to the other. That's a 5 followed by 17 zeros. If you could travel at the speed of light itself, which is impossible for anything with mass according to the laws of physics as we understand them, it would still take you 100,000 years to cross the galaxy. Human civilization as we know it, with cities and agriculture and writing, has existed for maybe 10,000 years at most. You would need to travel for 10 times the entire length of human civilization just to cross our galaxy. And you'd be traveling at the fastest speed possible in the universe. Our sun sits about 26,000 light years from the galactic center. We're not in any special location. We're not at the center, not at the edge, not in a particularly dense region or a particularly sparse one. We're in the suburbs of the galaxy, tucked into a minor spiral arm called the Orion Spur, located between two larger spiral arms called the Sagittarius Arm and the Perseus Arm. There's nothing remarkable about our position. We're just somewhere in the galactic disk, one star among hundreds of billions. At this scale, what is Earth? Consider this. There are more stars in the Milky Way than there are grains of sand on any single beach on Earth. Our sun is one grain on a beach, stretching 100,000 light years across. And Earth? Earth is a microscopic bacteria clinging to that single grain of sand. Invisible, undetectable, lost among hundreds of billions of other grains, each with their own potential worlds too small to see. The Milky Way is so vast that if you randomly threw a dart at our galaxy, the odds of hitting any star at all would be essentially zero. You'd hit empty space. The stars, as numerous as they are, occupy almost none of the galaxy's volume. And Earth? Earth orbits just one of those scattered points of light, are too small to register at any galactic scale. Let me give you more detail about our galaxy's structure because understanding it helps you grasp just how lost Earth truly is within it. The Milky Way is what astronomers call a barred spiral galaxy. This means it has a central bar-shaped structure made of densely packed stars with graceful spiral arms extending from the ends of the bar. If you could somehow fly above the Milky Way and look down on it, you'd see a pinwheel shape, bright at the center and trailing off into spiral arms that curve outward. Our sun is located in the Orion Spur, which is actually a minor arm, not one of the major spiral arms. It's more like a bridge connecting the Sagittarius Arm and the Perseus Arm. We're in a relatively sparse region of the galaxy, which is probably a good thing for life. Dense regions near the galactic center are chaotic and dangerous, filled with radiation and gravitational disturbances. The galaxy rotates, but not like a solid wheel. Different parts rotate at different speeds. Stars near the center orbit faster. Stars farther out orbit more slowly. This differential rotation is part of what creates and maintains the spiral arm structure. Our Sun takes about 225 million years to complete one orbit around the galactic center. Astronomers call this a galactic year or cosmic year. Think about what that means. In the time it takes for our Sun to go around the galaxy once, entire worlds can form and die. Entire species can evolve and go extinct. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge on Earth. The time before that, around 450 million years ago, life had barely crawled out of the oceans onto land. Fish were the most advanced vertebrates. Earth has been around for about 20 galactic years. The universe itself has only existed for about 60 galactic years. At the center of the Milky Way sits something remarkable and terrifying. A supermassive black hole called Sagittarius A star. This black hole has a mass of about 4 million times the mass of our Sun, all compressed into a region smaller than our solar system. The event horizon, the point of no return beyond which nothing can escape, is about 14 million miles across. That sounds large, but compared to the 4 million solar masses contained within it, it's incredibly compact. The region around Sagittarius A star is chaotic and violent. Stars whip around the black hole at incredible speeds. One star called S2 orbits the black hole once every 16 years, reaching speeds of up to 5% of the speed of light at its closest approach. 5% of light speed. That's about 33 million miles per hour, fast enough to cross from Earth to the Sun in about 3 hours. Fortunately, Earth is nowhere near this cosmic maelstrom. We're 26,000 light years from the galactic center, safely distant from the chaos. From our quiet suburb in the Orion Spur, the galactic center is just a bright region in the constellation Sagittarius, hidden behind clouds of dust and gas. The Milky Way has several distinct regions worth understanding. At the center is the galactic bulge, a dense spherical concentration of old stars about 10,000 light years across. The stars here are packed much more densely than in our neighborhood. If you lived on a planet near the galactic center, your night sky would be filled with thousands of brilliant stars. The darkness we experience at night would be replaced by something closer to perpetual twilight, with stars so numerous and bright that true darkness would never come. Surrounding the visible galaxy is the galactic halo, a roughly spherical region containing old stars and globular clusters. Globular clusters are dense balls of hundreds of thousands or even millions of ancient stars, among the oldest objects in the galaxy. Messier 13, the Great Globular Cluster in Hercules, contains about 300,000 stars packed into a region about 145 light years across. If you lived on a planet in the center of that cluster, you'd see thousands of stars as bright as Venus, filling your sky with light. The halo also contains dark matter, an invisible substance that we can detect only through its gravitational effects. The Milky Way's dark matter halo extends far beyond the visible galaxy, possibly out to 600,000 light years or more. Most of the Milky Way's total mass is actually dark matter, not the stars and gas and planets we can see. The Milky Way isn't alone in space. It has numerous satellite galaxies orbiting it, smaller galaxies caught in our gravitational pull. The two most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light. Both are being slowly torn apart by the Milky Way's gravity. Over billions of years, they'll be completely absorbed into our galaxy. Their stars scattered and mixed with ours. There are dozens of other smaller satellite galaxies, most of them dwarf galaxies containing only a few million stars. These tiny galaxies orbit the Milky Way like moths around a flame, gradually being pulled in and consumed. But here's where our perspective shifts again. Because the Milky Way, vast as it is with its hundreds of billions of stars and 100,000 light-year span, is just one galaxy among many. The nearest large galaxy to the Milky Way is Andromeda, also known as Messier 31. You can see Andromeda with your naked eye on a clear, dark night. It appears as a faint, fuzzy smudge in the constellation Andromeda. Most people who look at it have no idea they're seeing an entire galaxy, a structure containing 1 trillion stars, spanning 220,000 light-years across, more than twice the diameter of our own galaxy. Andromeda is about 2.5 million light-years away. That's 25 times the diameter of the Milky Way itself. The light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. When that light began its journey, modern humans didn't exist. Our ancestors were Australopithecus, early hominids just beginning to walk upright on the African savanna. The entire evolutionary journey from those early ancestors to modern humans happened while that light was traveling toward your eyes. Andromeda is actually larger than the Milky Way. It contains roughly 1 trillion stars, more than 3 times what our galaxy holds. It's the largest galaxy in our cosmic neighborhood, the dominant presence in our local region of space, and it's heading straight for us. Andromeda and the Milky Way are moving toward each other at about 250,000 miles per hour. In about 4.5 billion years, the two galaxies will collide and merge into a single, large, elliptical galaxy. But don't worry, when galaxies collide, the stars are so spread out that actual stellar collisions are extremely rare. It's more like 2 swarms of bees passing through each other than 2 solid objects crashing together. The galaxies will merge, their stars will mingle, but individual star systems like ours will likely survive intact. Together with about 50 other smaller galaxies, the Milky Way and Andromeda form what astronomers call the local group. This is our cosmic neighborhood, a cluster of galaxies bound together by gravity, moving through the universe as a unit. The local group spans about 10 million light-years across. Within it, the Milky Way is one of the 2 largest members. We're one of the giants in this particular crowd, but the local group itself is small. It's a minor gathering of galaxies in a universe that contains structures far, far larger. Let me try to put all of this in perspective. Earth orbits 1 star among 200 to 300 billion stars in the Milky Way. The Milky Way is 1 galaxy among roughly 50 in the local group. The local group spans about 10 million light-years. At the scale of nearby stars, just light-years away, Earth has already vanished. We're invisible from Alpha Centauri, undetectable from Sirius, completely unknown from Betelgeuse. The distances between stars are so vast that Earth disappears into the glare of the sun, lost, invisible, as if it doesn't exist. At the scale of the Milky Way, 100,000 light-years across, Earth has shrunk beyond any meaningful measurement. Our planet doesn't register. It doesn't exist at this scale in any practical sense. At the scale of the local group, 10 million light-years across, even the Milky Way begins to seem small. It's 1 galaxy among 50, 1 spiral among many. And Earth, already invisible within our galaxy, is so far below the threshold of existence that language fails to describe it. The light from the center of the Milky Way takes 26,000 years to reach Earth. That light left the galactic center around 24,000 BCE, when humans were still living as hunter-gatherers during the last ice age. Woolly mammoths roamed the frozen plains. Humans huddled in caves, painting images of animals on stone walls by flickering firelight. Agriculture hadn't been invented yet. Permanent settlements didn't exist. Writing wouldn't be invented for another 19,000 years. All of human civilization, everything we've built and discovered and created, has risen and fallen while that light has been traveling toward us. The Sumerians and Egyptians, the Greeks and Romans, the rise of Islam and Christianity, the Renaissance and Enlightenment, the Industrial Revolution and Space Age, all of it happened while that ancient light crossed the galaxy toward our tiny planet. And from the galactic center's perspective, none of it matters. Earth doesn't exist from that viewpoint. It's too small, too dim, too far away to ever be detected. We orbit an ordinary star in an unremarkable part of the galaxy, and even that star is just one point of light among hundreds of billions. The Milky Way doesn't know Earth exists. The stars don't know. The galaxy is a vast, ancient structure that has been rotating slowly for more than 13 billion years, long before Earth formed, long before our sun ignited. From the galaxy's perspective, we're nothing. A temporary arrangement of atoms on a tiny world orbiting an ordinary star. We appeared recently in cosmic terms, and will disappear eventually, and the galaxy will continue its slow rotation, completely unaware that we will ever hear. From the local group's perspective, we're even less than nothing. The Milky Way itself is just one galaxy among 50, and Earth is invisible even within our own galaxy. We are so small, so insignificant, that our existence barely registers at any scale larger than our immediate solar neighborhood. But here's what's humbling. We haven't even begun to explore the truly large structures of the universe. We've been discussing our immediate cosmic neighborhood, the stars nearby, our galaxy, the small cluster of galaxies we belong to. The universe extends far, far beyond this. There are structures out there that make the local group look like a speck of dust. There are voids and walls and filaments stretching across billions of light years. There are 2 trillion galaxies in the observable universe, and the observable universe might be just a tiny fraction of the total. When we start talking about galaxy clusters, superclusters, and the cosmic web that connects them all, the Milky Way itself begins to look small. Our galaxy, home to hundreds of billions of stars, becomes just another point in a pattern that spans the cosmos. And Earth doesn't just vanish at these scales. It reaches a level of smallness that challenges our ability to comprehend, that breaks the limits of language and mathematics, that makes even invisible and insignificant seem like overstatements. We're about to discover just how small that is. We've traveled from Earth's surface out past the moon, beyond the planets, through the vast emptiness of our solar system, past the nearest stars, and through the Milky Way's hundreds of billions of suns. We've seen Earth shrink from everything to less than nothing. But we're not done. Not even close. The Milky Way and its companion galaxies and the local group are just one tiny neighborhood in a much larger structure. To understand Earth's true insignificance, we need to explore the universe's largest features: galaxy clusters, superclusters, and the cosmic web that connects them all. We've already established that Earth is invisible from nearby stars and unmeasurable in any scale model of our galaxy. We've seen how the Milky Way, home to hundreds of billions of stars, is just one of about 50 galaxies in the local group. Now we're going to venture even further, into structures so vast that even our galaxy begins to look small. The local group, our cosmic neighborhood of about 50 galaxies, is part of something called the Virgo Supercluster. A supercluster is exactly what it sounds like. A cluster of galaxy clusters. Instead of talking about individual galaxies, we're now discussing groups of galaxy groups, all gravitationally connected in an enormous structure. Think about what that means. We started with Earth, one planet. Then we zoomed out to the solar system, one star with its planets. Then to the Milky Way, hundreds of billions of stars. Then to the local group, about 50 galaxies. Now we're talking about structures that contain thousands of galaxy groups, each containing dozens or hundreds of galaxies, each containing billions or trillions of stars. The scale keeps multiplying. Each level up doesn't just add a little more space, it multiplies the previous scale by factors of hundreds or thousands or millions. The Virgo Supercluster contains at least 100 galaxy groups and clusters. Its dominant feature is the Virgo cluster, a massive collection of roughly 1,000 to 2,000 galaxies located about 54 million light-years from Earth. The Virgo cluster is the heart of our supercluster, the gravitational anchor around which everything else orbits. 54 million light-years. Let me put that in perspective. The light we see from the Virgo cluster tonight left those galaxies 54 million years ago, when dinosaurs had already been extinct for about 12 million years. Early primates were just beginning to evolve. The continents were still shifting toward their current positions. India was crashing into Asia, pushing up the Himalayas. The world was unrecognizable, and all the time, that light has been traveling toward us through the void, crossing the emptiness between galaxy clusters to finally reach our telescopes tonight. Some of the galaxies in the Virgo cluster are enormous. Messier 87, a giant elliptical galaxy at the cluster's heart, contains about 1 trillion stars. That's roughly 4 times what the Milky Way has. If the Milky Way is a large city, Messier 87 is a sprawling megalopolis, a cosmic Tokyo or Shanghai dwarfing everything around it. Messier 87 also has a supermassive black hole at its center, with a mass of about 6.5 billion times the mass of our Sun. For comparison, the black hole at the center of the Milky Way, Sagittarius a star, is only about 4 million solar masses. Messier 87's black hole is more than 1,600 times more massive than ours. It's one of the largest black holes ever discovered, a monster lurking at the heart of a monster galaxy. In 2019, astronomers captured a first ever image of a black hole, and it was Messier 87's black hole they photographed. That fuzzy orange ring that made headlines around the world, that groundbreaking image that proved black holes look like Einstein's equations predicted, that was the shadow of a void 6.5 billion times more massive than our Sun, sitting at the center of a galaxy 54 million light-years away. The Virgo supercluster as a whole spans approximately 110 million light-years across and contains around 100 trillion stars. Remember, the Milky Way is about 100,000 light-years across. The Virgo supercluster is more than 1,000 times larger than our entire galaxy. 1,000 times larger. If the Milky Way were a dinner plate, the Virgo Supercluster would be a space about 3 football fields long. Everything we discussed about our galaxy, all those hundreds of billions of stars, all that vast spiral structure, it would fit on a dinner plate in a space stretching hundreds of yards. In this supercluster, the Milky Way is just one galaxy among perhaps 10,000 others. We're not even a particularly large galaxy within this structure. Several galaxies in the Virgo cluster are significantly larger than the Milky Way. We're average at best, unremarkable, one spiral among thousands. If the Virgo supercluster were shrunk to the size of a city, the Milky Way would be smaller than a single house. Actually, it would be more like a single room in one of those houses. One room in one house in an entire city of structures. And Earth? Earth would be so small within that room that no measurement could capture it. You'd need to zoom in past the atomic level, past the subatomic level, to find anything representing our planet. But here's where things get truly mind-bending. In 2014, astronomers made a discovery that redrew the map of our cosmic neighborhood entirely. They found that the Virgo supercluster, this enormous structure we'd been studying for decades, is just a small lobe of an even more massive structure. They called it Laniakea. Laniakea comes from Hawaiian, meaning immeasurable heaven. The name was chosen by Nawa'a Napoleon, a Hawaiian language professor, at the request of the astronomers who discovered it. It's an appropriate name because Laniakea is almost incomprehensibly vast, a heaven that truly seems beyond measurement. This supercluster of superclusters contains approximately 100,000 galaxies spread across 520 million light years. 520 million light years. The light crossing from one edge of Laniakea to the other would need 520 million years to make the journey. When that light started traveling, the most complex life on Earth was still in the oceans. Fish were just beginning to develop jaws. Nothing had crawled onto land yet. All these galaxies, all 100,000 of them, including our Milky Way, are slowly flowing toward Laniakea's center. They're drawn by the combined gravitational pull of all that mass, like water flowing downhill toward a drain. We're falling, all of us, our entire galaxy, toward a point in space we can barely see. The gravitational center of Laniakea is a region called the Great Attractor. For decades, astronomers knew something massive was out there. When they measured the motion of galaxies in our region of space, they found that everything was moving in a particular direction, as if being pulled by something enormous. But when they tried to look in that direction, they couldn't see anything. The Great Attractor sits behind the plane of the Milky Way from our perspective, hidden behind clouds of dust and gas and billions of stars in our own galaxy. It was like knowing there's a waterfall ahead by the sound of the roar, but being unable to see it because of fog. Something massive was pulling us, but we couldn't see what. Using different types of light that can penetrate the dust, radio waves, infrared, X-rays, astronomers have pieced together what the Great Attractor actually is. It's not a single object. It's a region containing several massive galaxy clusters, including the Norma cluster, one of the largest concentrations of galaxies in our cosmic neighborhood. The combined mass of these clusters creates a gravitational pull strong enough to influence the motion of thousands of galaxies across hundreds of millions of light years. But even the Great Attractor isn't the whole story. Recent observations suggest there's something even more massive beyond Laniakea. Something pulling on the Great Attractor itself. The Shapley Supercluster, located about 650 million light years away, contains thousands of galaxies, and has a total mass of about 10,000 trillion times the mass of the Sun. That's a 1 followed by 16 zeros. Solar masses. The combined gravity of the Shapley Supercluster appears to be pulling Laniakea and everything in it. We're not just flowing toward the Great Attractor, we're part of a larger flow moving toward an even greater concentration of mass beyond. It's cosmic gravity all the way down, larger structures pulling on smaller structures, pulling on even smaller structures, in a hierarchy of gravitational influence, spanning billions of light years. Let me try to put Laniakea's scale in perspective. The Milky Way is about 100,000 light years across. Laniakea is about 5,200 times larger. If the Milky Way were shrunk to the size of a coin, a quarter, Laniakea would span about the length of a football field. An entire football field, 100 yards of space, with our galaxy as a single coin somewhere in that expanse. In that football field model, where would Earth be? Earth would be a bacterium on that coin, present technically, but functionally invisible, non-existent for all practical purposes. But we're still not at the largest structures. Let me tell you about the cosmic web. When astronomers map the distribution of galaxies across the universe, they find something remarkable. Galaxies aren't randomly scattered through space like salt sprinkled on a table. Instead, they cluster along filaments, forming a vast cosmic web. These filaments are threads of matter, strings of galaxies and dark matter stretching across billions of light years. Between the filaments are enormous voids, regions where very few galaxies exist. If you could somehow zoom out far enough to see the entire observable universe at once, you'd see something that looks almost organic. It looks like the neural network of a brain, or the structure of a sponge, or the pattern of veins in a leaf. Thin threads of light connecting dense nodes, with vast dark spaces between them. It's one of the most beautiful patterns in existence, and it spans the entire cosmos. The cosmic web is the largest pattern in the universe. It emerged from tiny density fluctuations shortly after the Big Bang. In the first moments of the universe's existence, quantum fluctuations created regions that were very slightly denser than average, and regions that were very slightly less dense. The differences were tiny, perhaps 1 part in 100,000. But over billions of years, gravity amplified these differences. Denser regions pulled in more matter from their surroundings, becoming denser still. Less dense regions lost matter to their neighbors, becoming emptier. It's like how small variations in a hillside can become deep valleys and high ridges after millions of years of erosion. The slight initial differences grew and grew until they became the structure we see today. The result is the cosmic web. Filaments of galaxies stretching for hundreds of millions or billions of light years, connected at nodes where galaxy clusters form, and between them, voids. Vast empty spaces where almost nothing exists. The filaments contain most of the matter in the universe, concentrated into these thin threads, while the voids contain almost nothing. Vast bubbles of emptiness between the threads. Let me tell you about some of these structures. The Sloan Great Wall, discovered in 2003 by astronomers analyzing data from the Sloan Digital Sky Survey, is a filament of galaxies stretching about 1,370,000,000 light years. That's nearly 14,000 times larger than the Milky Way. If the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. A grain of rice in a structure stretching more than 1,000 yards. That's the scale we're dealing with now. The Sloan Great Wall contains tens of thousands of galaxies, each containing billions or trillions of stars. It's not a solid wall, of course. It's more like a cosmic membrane, a sheet of galaxies relatively thin compared to its length and width, but still enormously thick by any human standard. The galaxies within it are gravitationally connected, part of the same large-scale structure, all flowing together through the cosmos. Then there's the CFA2 Great Wall, discovered earlier in 1989. This is another filament of galaxies about 500 million light-years long, 200 million light-years wide, and 15 million light-years thick. It's smaller than the Sloan Great Wall, but still enormous, still containing tens of thousands of galaxies, still spanning distances that light needs hundreds of millions of years to cross. The Virgo Supercluster, which contains the Milky Way, is actually part of this structure. So in a sense, we live on one of these cosmic walls. We're embedded in a filament of the cosmic web, part of a structure stretching hundreds of millions of light years across the universe. But the Milky Way is just one tiny galaxy among tens of thousands that make up the wall. We're a single brick in an enormous structure, a single thread in a cosmic tapestry. But these walls aren't even the largest structures. The Hercules-Corona Borealis Great Wall, discovered in 2013, might be the largest known structure in the universe. It's a galactic filament stretching approximately 10 billion light-years across. 10 billion light-years. Let that sink in. The Milky Way is 100,000 light-years across. The Hercules-Corona Borealis Great Wall is 100,000 times larger. If the Milky Way were a coin, this structure would span more than 15 miles. If the Milky Way were a grain of sand, this structure would stretch from New York to Chicago. If you traveled at the speed of light, it would take you 100,000 years to cross the Milky Way. It would take you 10 billion years to cross the Hercules-Corona Borealis Great Wall. The universe itself is only 13.8 billion years old. You would need to travel for more than 70% of the age of the universe at the fastest speed possible just to cross one structure within it. At these scales, the Milky Way doesn't just become small, it becomes unmeasurable. It becomes a rounding error. A galaxy that seemed vast when we were counting its hundreds of billions of stars is now just one point among billions of other points in a web that spans the universe. Our galaxy has the same significance in this structure that a single bacterium has in your body. Technically present, but so small that it changes nothing, affects nothing, means nothing to the larger whole. The existence of structures this large actually created a problem for cosmologists. According to our understanding of how the universe evolved, there shouldn't be enough time for structures this large to form. The universe is only 13.8 billion years old. Gravity works slowly. It takes time for matter to clump together into galaxies, more time for those galaxies to cluster into groups, even more time for those groups to form superclusters and filaments. Computer simulations of the universe's evolution, running the physics forward from the Big Bang to today, predicted that the largest structures should be no more than 1.2 billion light-years across. That's already enormous, but the Hercules-Corona Borealis Great Wall is roughly 10 times larger than that. How did something so large form in only 13.8 billion years? We don't know. Its existence suggests that either our models are wrong or incomplete, or that the universe is stranger than we thought. Perhaps gravity works differently at these scales. Perhaps there's physics we haven't discovered yet. Perhaps the initial conditions of the universe were different than we assumed. The Hercules-Corona Borealis Great Wall is a mystery. A structure that shouldn't exist according to our best theories, and yet there it is, stretching across a significant fraction of the observable universe. Now let me tell you about the voids, because the emptiness is just as important as the fullness. Between the filaments of the cosmic web are vast regions where almost nothing exists. These cosmic voids are enormous bubbles of emptiness, hundreds of millions of light years across, containing very few galaxies. If the filaments are the threads of the web, the voids are the spaces between the threads, the gaps that make the pattern visible. The Boötes Void, discovered in 1981, is approximately 330 million light years in diameter. It's so empty that for years, astronomers found only 60 galaxies within it. 60 galaxies in a volume that should contain thousands. Later surveys found a few more, but the void remains remarkably empty, a bubble of almost nothing in the cosmic foam. The KBC void, named after the astronomers who studied it, is even larger, approximately 2 billion light years in diameter. Some astronomers believe our own local group sits near the edge of this void, which might explain some anomalies in our measurements of the universe's expansion. We might be living in an unusually empty region of space, a cosmic backwater far from the dense filaments where most matter congregates. These voids make up most of the universe's volume. When you add up all the empty space, all the voids and gaps and regions of near nothingness, they dominate the cosmos. Most of space is empty. The galaxies and clusters and filaments, for all their billions of stars, are exceptions in an ocean of nothing. This means that if you teleported to a random point in the universe, you would almost certainly find yourself in a void, surrounded by nothing, with the nearest galaxy hundreds of millions of light years away. The universe is mostly empty, and the matter within it is concentrated into thin threads and scattered nodes, islands of something in an ocean of nothing. Now let's push to the ultimate limit. Let's talk about the observable universe itself. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is approximately 13.8 billion years old. Light has been traveling toward us for all that time, but because the universe has been expanding while the light was traveling, the observable universe is larger than 13.8 billion light years across. This is a subtle but important point. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. While the light was traveling toward us, space itself was expanding, stretching the distance. By the time the light arrives, the galaxy has moved much farther away. It's like running on a treadmill that's moving backward. You run forward, but the belt carries you back, so your actual distance from the starting point is greater than the distance you ran. The result is that the observable universe is about 93 billion light years in diameter. The most distant objects we can see are now about 46 billion light years away, even though the light from them has only been traveling for about 13 billion years. Space expanded while the light was in transit. Within this observable volume, astronomers estimate there are approximately 2 trillion galaxies. 2 trillion. That's a 2 followed by 12 zeros. 2,000 billion. 2 million million. If you counted one galaxy per second, it would take you 63,000 years to count them all. Every civilization humanity has ever built would rise and fall many times over before you finish counting. Each of those 2 trillion galaxies contains anywhere from millions to trillions of stars. Small dwarf galaxies might have only a few million stars. Giant ellipticals like Messier 87 contain 1 trillion or more. The average is probably somewhere around 100 billion stars per galaxy. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros, 200 sextillion. A number so large it loses all meaning, a number beyond human comprehension. Here's a way to grasp it. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth. Not just one beach, all the beaches. Every grain of sand on every beach on every continent. And there are still more stars than that. About 10 times more, actually. And the Milky Way is one of those 2 trillion galaxies. Our galaxy isn't particularly special. It's not the largest. It's not the smallest. It's not in a particularly dense region or a particularly empty one. It's just one ordinary spiral galaxy among 2 trillion others, indistinguishable from the crowd. If every galaxy were represented by a single grain of sand, you would need enough sand to fill several Olympic-sized swimming pools. The Milky Way would be one grain in that vast pile. You could search for years and never find it. You could sift through handful after handful and never encounter your home galaxy. And Earth? Earth orbits one star among approximately 300 billion stars in the Milky Way, which is one galaxy among approximately 2 trillion galaxies in the observable universe. Let me do the math. There are approximately 200 billion trillion stars in the observable universe. Earth orbits one of them. If you randomly selected a star from the observable universe, the probability of selecting our sun is 1 in 200 billion trillion. That's a probability of 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 23 zeros after the decimal point before you get to a non-zero digit. For all practical purposes, that's 0. The odds of randomly selecting Earth from all the matter in the observable universe are essentially 0. Not unlikely, not improbable, essentially impossible. Here's the comparison I've been building toward. If the observable universe were shrunk to the size of Earth, just under 8,000 miles in diameter, the Milky Way would be smaller than a single atom. Our entire galaxy, with all its hundreds of billions of stars, all its spiral arms and globular clusters and dark matter halo, would be smaller than a hydrogen atom in an Earth-sized model of the universe. And Earth? In a scale model where the universe is Earth-sized, Earth itself would be smaller than any particle physics has ever detected. Smaller than quarks, the fundamental building blocks of protons and neutrons. Smaller than any theoretical particle we've ever proposed. It would occupy a volume so small that it literally doesn't exist in any meaningful sense. Mathematics can describe it, but nothing physical can represent it. This is the only time I'll make this comparison, because it's the only scale where it truly lands. At the level of the observable universe, Earth achieves a smallness that human language was never designed to express. But here's what makes this even more striking. The observable universe is just what we can see. It's not the whole universe, it's just the part from which light has had time to reach us. We can't see beyond the observable universe because light from anything farther away hasn't had time to reach us yet. There's a horizon beyond which we cannot see, not because we lack powerful enough telescopes, but because the universe simply isn't old enough for light from those regions to have reached us. It's like standing on a ship in the middle of the ocean. You can see to the horizon, but you know the ocean extends beyond it. The horizon isn't the edge of the ocean. It's the edge of what you can see. Cosmologists estimate that the actual universe might be at least 250 times larger than the observable universe. Some calculations suggest it could be much larger than that. Some theories suggest it might be infinite, extending forever in all directions, with no edge, no boundary, no end. If the universe is 250 times larger than what we can observe, then the observable universe is less than 0.5% of the total. Everything we've ever seen, every galaxy we've ever photographed, every star whose light has reached our telescopes, all of it is a tiny bubble in a vastly larger cosmos. If the universe is infinite, then the observable universe, vast as it is essentially nothing. 0% of infinity is still zero. No matter how large a finite region is, it's still infinitely smaller than an infinite whole. Our galaxy, already smaller than an atom in scale models of the observable universe, becomes infinitely small in an infinite universe. The concept of relative size breaks down entirely. And Earth? In an infinite universe, Earth is so small that there are no comparisons left. Every analogy fails. Every scale model becomes meaningless. Earth is simply infinitely small, which is to say it has no size at all from the universe's perspective. It's a mathematical point, a location with no volume, a position without extent. We've now compared Earth to every category of object the universe contains. Planets, stars, galaxies, superclusters, the cosmic web, the observable universe itself. At every scale, Earth has diminished, but there's one comparison left. The strangest one of all. We've been comparing Earth to things, to objects, to matter, but most of the universe isn't matter. Most of the universe is empty space, void, vacuum, nothing. What happens when we compare Earth to the nothing itself? We've traveled across the universe, watching Earth shrink from everything we know to something unmeasurably small. We've compared it to planets, stars, galaxies, and the largest structures in existence. At every scale, Earth has diminished until it effectively disappeared. We started this journey standing on what seemed like solid, endless ground. Earth felt vast, permanent, the foundation of everything. Then we compared it to Jupiter and watched it shrink to less than 1,000th of that giant planet's volume. We compared it to the sun and watched more than 1 million Earths disappear into that blazing sphere. We ventured past the stars and watched Earth vanish entirely, invisible from even our nearest stellar neighbors. We zoomed out through the Milky Way and saw our entire solar system become unmeasurable. We explored superclusters and the cosmic web until even our galaxy became a speck among 2 trillion others. But there's one final comparison to make. One that might be the most profound of all. We need to compare Earth to the emptiness of space itself. Because the universe isn't filled with matter. The universe is overwhelmingly, almost entirely, empty. Let's start with a simple fact. The universe is about 99.99999999999999999% empty space. I didn't stutter. That's 25 nines after the decimal point, and even that might be an underestimate. Most of the universe is void. Vacuum, nothing. The galaxies, stars, planets, and all the matter we've discussed occupy an almost infinitesimally small fraction of the total volume of space. everything that exists, every atom of every object in the entire cosmos, is like a few specks of dust floating in an empty warehouse the size of a continent. This emptiness exists at every scale, from the largest structures down to the smallest particles. No matter how far you zoom in or zoom out, you find the same thing. Mostly nothing, with occasional islands of something scattered through the void. Let's start with the cosmic voids, the largest empty spaces in existence. Remember the cosmic web we just discussed? The network of galaxy filaments stretching across the universe? Between those filaments are enormous regions called voids, where very few galaxies exist. These aren't just empty spaces. They're vast bubbles of almost nothing, volumes so empty and so large that they dwarf the matter within them. The KBC void, one of the largest known voids, is approximately 2 billion light years in diameter. 2 billion light years of mostly nothing. If you could somehow stand at the center of this void and look around, you would see almost nothing. A few scattered galaxies in the far distance, like lonely ships on an ocean that stretches beyond the horizon in every direction. The void is so vast that light from one side takes 2 billion years to reach the other. Entire civilizations could rise, flourish, and vanish while a photon crosses this emptiness. And the KBC void is just one of many. The universe is filled with these voids. The Boötes Void, about 330 million light years across, contains so few galaxies that when it was first discovered, astronomers thought their instruments must be malfunctioning. How could there be so much nothing in one place? But the instruments were working fine. The void was real. It was just empty. The giant void, discovered in the constellation Canes Venatici, stretches about 1,200,000,000 light years across. The cold spot, a region in the cosmic microwave background radiation that appears cooler than its surroundings, might be caused by a supervoid perhaps 1,800,000,000 light years in diameter. These are regions where almost nothing exists, where space stretches on and on and on with barely any matter to interrupt it. Voids make up approximately 80% of the universe's volume. Let that sink in. 80%. 4/5 of all the space in the cosmos is essentially empty. The galaxies and clusters and filaments we've been discussing, all that structure we mapped, exist in just 20% of the total volume. This means that all the matter in the universe, every galaxy and star and planet, exists in a small fraction of the total space available. Through that matter, everything that shines and orbits and exists occupies only about 1/5 of the universe's volume. The rest is void. And Earth? Earth is a tiny fraction of the matter that exists, in that small fraction of the universe that isn't void. We're a minority of a minority of a minority. A speck within the speck of matter that floats through an ocean of nothing. If you randomly teleported to a location in the universe, you would almost certainly appear in a void. You would find yourself floating in complete darkness, with no stars visible, no galaxies detectable, nothing but emptiness stretching for hundreds of millions of light years in every direction. The matter-filled regions we've been discussing, the places where stars shine and planets orbit, those are the exceptions. The emptiness is the rule. But the emptiness goes deeper than cosmic voids. Let's zoom in and look at the space between stars, within galaxies, even within the Milky Way, even in the matter-filled regions of the universe. Most of the volume is empty space. Stars are separated by enormous distances. The matter is scattered thinly, like individual grains of sand spread across a vast desert. Our nearest stellar neighbor, Proxima Centauri, is 4.24 light-years away. We discussed this earlier. That's about 25 trillion miles of mostly nothing between us and the closest star. 25 trillion miles of vacuum, with perhaps a few atoms of hydrogen per cubic centimeter drifting through the void. That's not empty by laboratory standards, but it's as close to nothing as anything in the universe gets. The interstellar medium, the space between stars, contains roughly 1 atom per cubic centimeter. For comparison, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. The space between stars is 25 billion trillion times emptier than the air around you. And that's not even true vacuum. True vacuum, like the voids between galaxy clusters, is emptier still. The Milky Way contains somewhere between 200 and 400 billion stars, but those stars are spread across a volume 100,000 light-years across. If you flew through the galaxy in a perfectly straight line, the odds of hitting a star would be almost zero. You could cross the entire galaxy, all 100,000 light-years of it, and pass nothing but empty space. When galaxies collide, as the Milky Way and Andromeda will in about 4.5 billion years, the stars almost never actually hit each other. The spaces between stars are so vast relative to the sizes of the stars themselves that the galaxies pass through each other like 2 swarms of gnats. The gnats don't collide because there's so much empty space between them. Even in a galaxy merger, the emptiness dominates. The Milky Way is mostly empty space, with a few 100 billion stars scattered throughout like grains of salt thrown into a sports arena. The arena looks full if you're standing among the salt grains, but from outside you'd see mostly empty air with occasional white specks. But let's go even smaller. Let's look at the solar system. We discussed earlier how the solar system is mostly empty space, but let me emphasize just how empty that space actually is. The solar system, from the Sun to the Oort cloud, spans roughly 2 light-years. That's about 12 trillion miles in diameter. The Sun itself is about 864,000 miles in diameter. The ratio between these numbers is staggering. If you calculate the volume of a sphere encompassing the entire solar system and compared it to the volume of all the matter within that sphere, you would find that the matter occupies an almost immeasurably small fraction. The Sun, which contains 99.86% of the solar system's mass, occupies far less than 1/1,000,000,000% of the solar system's volume. All the planets combined, all the moons, all the asteroids and comets and dust, everything except the Sun, adds up to only 0.14% of the solar system's mass. And even that tiny amount of additional mass is spread across trillions of cubic miles of space. The solar system is overwhelmingly empty. If you could somehow color all the matter in the solar system red and all the empty space blue, the solar system would appear solid blue with a tiny red dot at the center, representing the Sun, and invisible red specks representing the planets. Earth's position in this emptiness is telling. We orbit at about 93 million miles from the Sun. Imagine a sphere centered on the Sun with a radius of 93 million miles, a sphere just large enough to contain Earth's orbit. The volume of that sphere is approximately 3.4 sextillion cubic miles. And Earth occupies about 260 billion cubic miles of that volume. That means Earth occupies about 1/13 millionth of the volume of the sphere that encompasses our orbit. Less than 1 part in 10 million. The rest of that sphere, more than 99.9999% of it, It is empty space. We're not orbiting through a region filled with matter. We're orbiting through almost complete emptiness, a tiny grain of rock tracing a path through the void, held in orbit by the gravity of a star 93 million miles away. But we can go smaller still, much smaller, because the emptiness isn't just between objects, it's inside them. Let's look at the emptiness within matter itself. Atoms, the building blocks of everything, including Earth, including you, are themselves almost entirely empty space. This might be the most surprising fact in all of physics. The solid matter you touch, the ground you stand on, the body you inhabit, all of it is mostly nothing. An atom consists of a tiny nucleus made of protons and neutrons, surrounded by a cloud of electrons. But the nucleus is extraordinarily small compared to the atom as a whole, almost incomprehensibly small. If an atom were enlarged to the size of a football stadium, the nucleus would be about the size of a marble, sitting at the center of the 50-yard line. The electrons would be like gnats buzzing around somewhere in the upper decks. And the rest of the stadium, all the seats, all the field, all the space from floor to ceiling, would be completely empty. Just air, nothing. More than 99.9999% of an atom's volume is empty space. The actual matter, the protons and neutrons in the nucleus, occupies less than 1/trillionth of the atom's total volume. The electrons contribute even less because they're so much smaller than protons and neutrons. This means that solid matter isn't really solid. Not at all. When you touch a table, you're not actually touching the table's atoms. Your atoms and the table's atoms never actually contact each other. What you feel as solid, the resistance you experience when you push against something, is actually electromagnetic repulsion between the electron clouds of your atoms and the object's atoms. The electrons in your finger repel the electrons in the table, and that repulsion feels like solidity. But the atoms never touch. The nuclei, where almost all the mass resides, are separated by vast, relatively speaking, distances. You have never truly touched anything in your life. You've only felt electromagnetic forces pushing back against you. Everything you've ever touched, everyone you've ever held, every solid object you've ever encountered, it's all mostly empty space. The atoms that make up matter are themselves almost entirely nothing. Void pretending to be substance. Emptiness masquerading as solidity. And what does this mean for Earth? Earth is made of atoms. Approximately 1.33 times 10 to the 50th power atoms. Give or take. That's a 1 followed by 50 zeros. A number so large that there's no way to visualize it. More atoms than there are stars in the observable universe. More atoms than there are grains of sand on all the beaches on all the planets that might have beaches in the cosmos. But each of those atoms is more than 99.9999% empty space. The matter in each atom, the protons and neutrons and electrons that constitute actual stuff, occupies only a tiny fraction of the atom's volume. This leads to a startling conclusion. If you could somehow remove all the empty space from Earth's atoms, if you could compress all the protons, neutrons, and electrons together until they actually touched, Earth would shrink dramatically. The entire planet, all 7.9 sextillion tons of it, would compress down to a sphere less than a mile in diameter. Let me say that again. All of Earth, every mountain and ocean, every continent and island, every city and forest and desert, every living creature, every building, every grain of sand and drop of water, all of it, compressed until the atomic nuclei actually touched, would fit in a sphere smaller than many cities. The Earth, nearly 8,000 miles in diameter, is almost entirely empty space. What seems solid is mostly void. What seems substantial is mostly nothing. The ground beneath your feet is a lattice of atomic nuclei, floating in a sea of electromagnetic forces, with vast, relatively empty spaces between them. This is what happens to matter when it compresses to nuclear densities. Neutron stars, the collapsed remnants of massive stars that have exploded, are made of matter compressed to this degree. A neutron star contains about 1.5 times the mass of the Sun, but it's only about 12 miles across. That's what matter looks like when you remove the empty space from atoms. A teaspoon of a neutron star material would weigh about 6 billion tons on Earth. Earth could become a neutron star's worth of matter, but compressed to nuclear density, it would be less than a mile across. That's how much empty space is inside the atoms that make up our planet. That's how much nothing is within the something. So when we ask how small Earth really is, we need to recognize that Earth isn't just small compared to other objects. Earth is mostly empty space itself. The matter that makes up our planet, the actual stuff as opposed to the void between atomic nuclei, would fit in a sphere less than a mile across. That tiny ball of compressed matter is floating in the mostly empty solar system, which is floating in the mostly empty galaxy, which is floating in the mostly empty supercluster, which is floating in the mostly empty universe. Consider the layers of emptiness surrounding you right now. You're made of atoms that are mostly void. You stand on a planet that's mostly empty atomic space. That planet floats in a solar system that's overwhelmingly vacuum. That solar system drifts through a galaxy that's almost entirely nothing, between stars. That galaxy sits in a universe where 80% of all space is cosmic void. It's emptiness all the way down and all the way up. Every level of reality is dominated by nothing, and Earth is a brief interruption in that nothing. It's self-composed of the same void it floats within. This is what I mean by Earth being smaller than nothing. The emptiness of space, the voids and vacuums that fill the universe, vastly exceed all the matter that exists. Earth isn't just small compared to the universe's contents. Earth is small compared to the universe's emptiness. The nothing is bigger than the something. The void is more substantial than the matter. And Earth is a tiny speck of mostly empty matter floating in that infinite void. If this seems abstract, let me make it concrete. In 1990, the Voyager 1 spacecraft, which had completed its primary mission of exploring Jupiter and Saturn and was heading out of the solar system, turned its camera back toward Earth and took a photograph. At the request of the astronomer Carl Sagan, NASA commanded the spacecraft to capture one last image of home before it traveled too far to see us anymore. The result was an image that has come to be known as the pale blue dot. In that photograph, Earth appears as a tiny point of light, less than a single pixel in size, suspended in a beam of sunlight. It's not blue in any striking way. It's not obviously a planet. It's just a speck, a mote, a barely visible dot in the vast darkness. That photograph was taken from about 3.7 billion miles away. That sounds far, and it is by human standards, but on cosmic scales, it's nothing. 3.7 billion miles is barely out of the solar system. It's not even to the Kuiper belt yet, let alone the Oort cloud. It's a tiny fraction of the distance to the nearest star. And already, Earth had shrunk to less than a pixel. Carl Sagan reflected on this image in his book, also called pale blue dot. His words are worth considering. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every king and peasant, every hero and coward, every creator and destroyer of civilization, every saint and sinner in the history of our species lived on that mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena, Sagan wrote. Think of the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. That photograph was taken from within our own solar system, before Voyager had even reached interstellar space. From the nearest star, Earth would be completely invisible. From another galaxy, the entire solar system would vanish. From the other side of the cosmic web, the Milky Way itself would be just another faint smudge among billions. And yet, that pale blue dot is home. Everything that has ever mattered to any human being happened there. Every love story and every tragedy, every discovery and every loss, every moment of joy and every moment of despair, all of it, confined to that tiny speck that barely registers in a photograph taken from a few billion miles away. Let me bring this journey to a close with some perspective on what all this means. We started with Earth as everything. The ground beneath our feet and the sky above, the horizon stretching to what seems like infinity. From a human perspective standing on its surface, Earth seems vast, incomprehensibly large, more than anyone could explore in a lifetime. And then we zoomed out. We compared Earth to the moon, to the planets, to the sun that dominates our solar system. We ventured past the stars to our galaxy, out through the local group, to the superclusters, the cosmic web, the observable universe itself. At every step, Earth shrank, from a large planet to a small one, from a visible world to an invisible speck, from a detectable object to something unmeasurably tiny, from a presence to an absence, from something to essentially nothing. And then we went further. We compared Earth not just to the matter in the universe, but to the emptiness that makes up most of existence. We discovered that Earth is small not only compared to stars and galaxies, but compared to the voids and vacuums that dominate the cosmos. We found that Earth itself is mostly empty space, that the solid ground we stand on is a cloud of atoms that are themselves almost entirely nothing. Earth, in the final analysis, is smaller than nothing. The emptiness of space exceeds all matter. The void dwarfs all substance. And Earth is a tiny arrangement of mostly empty atoms floating in an ocean of nothing that stretches for billions of light years in every direction. This could be depressing. This could make us feel worthless, insignificant, pointless. If Earth is so small, if we're so tiny in the cosmic scheme of things, what does any of it matter? But I want to suggest a different perspective. The universe is vast and ancient and mostly empty. Galaxies spin through the void, stars burn and die, matter and energy flow according to physical laws that have operated since the beginning of time. The cosmos has been doing its thing for 13.8 billion years, and it will continue for trillions more, but none of it knows it exists. The stars don't know they're shining, the galaxies don't know they're spinning, the voids don't know they're empty. The universe, for all its vastness and complexity and grandeur, is unconscious. It has no awareness of itself. It simply is, operating according to physical laws with no understanding of what it's doing or why. But somewhere in all that vastness, on a tiny planet orbiting an ordinary star in an unremarkable galaxy, something remarkable happened. Atoms arranged themselves into structures that can know, that can wonder, that can look up at the night sky and feel awe at the scale of it all. We are the universe, knowing itself. We are matter, contemplating matter. We are the cosmos, becoming aware of its own existence, its own vastness, its own beauty and terror and indifference. Think about what that means. The universe existed for about 9 billion years before Earth even formed. For most of that time, as far as we know, there was no one to see it. Galaxies formed and merged and scattered. Stars ignited and burned and exploded. The cosmic web took shape across billions of light years. All of it happened in silence, in darkness, without witness. And then, on a tiny planet around an ordinary star, carbon and hydrogen and oxygen and nitrogen arranged themselves into molecules that could replicate. Those molecules evolved into cells. Those cells evolved into organisms. Those organisms evolved into creatures that could think, that could wonder, that could ask questions about the universe they found themselves in. For the first time in 13.8 billion years, the universe had eyes, it had minds, it had beings capable of looking back across all that space and time and understanding, at least partially, what they were seeing. You are one of those beings. When you look up at the night sky, you're seeing the universe. The stars you see are other suns, many larger than ours. The darkness between them is void stretching for light years. The faint glow of the Milky Way is the combined light of billions of stars too distant to resolve individually. And you're seeing it. You're understanding it. A human being on a tiny planet around an ordinary star, looking out at the cosmos and grasping, at least in part, what you're looking at. That's remarkable. That might be the most remarkable thing in the entire universe. Not the vastness, not the emptiness, not the billions of galaxies or the trillions upon trillions of stars. What's remarkable is that you're here to witness it. That matter has become conscious of itself. That the universe has produced beings capable of asking how small they really are. Earth is tiny. Incomprehensibly tiny. Smaller than nothing in the cosmic scheme. But Earth is also precious. Perhaps infinitely precious. Because as far as we know, Earth is the only place where all this emptiness has produced something that can appreciate it. The only location where the void has given rise to beings capable of measuring the void. We might not be alone. There might be other planets with other life forms looking up at their own night skies and wondering about their own smallness. We haven't found them yet, but the universe is vast, and we've barely begun to look. Perhaps consciousness is common, emerging wherever conditions permit. Perhaps the universe is filled with minds contemplating minds. Or perhaps we're alone. Perhaps Earth is the only place where the cosmic accident of consciousness has occurred. Perhaps in all the billions of galaxies and trillions of stars and quintillions of planets, we are the only ones who have ever looked up and wondered. Either way, what we have here is precious. This tiny world, this pale blue dot, this speck of mostly empty atoms in an ocean of void. It's home. It's where consciousness emerged. It's where beings like us can love and laugh and create and dream. The next time you step outside on a clear night, look up. See the stars scattered across the darkness. Know that each one is a sun, many larger than ours. Know that the darkness between them stretches for unimaginable distances. Know that beyond what you can see, there are billions of galaxies containing trillions of stars. And then look down at the ground beneath your feet. This is Earth, this tiny world, this speck of mostly empty atoms in an ocean of nothing. And you're here, standing on it, looking up, wondering. That's the miracle, not the vastness of space, not the emptiness of the void, but you, here, now, aware of it all. Earth is small. Earth is smaller than we can truly comprehend. Earth is smaller than nothing. But Earth is also everything we have. The only home we've ever known. The only place in the universe where we know for certain that life exists. That consciousness exists. That beings can look up at the stars and ask what it all means. That makes Earth precious beyond measure. Not because it's large or important in cosmic terms, but precisely because it's so small and rare and unlikely. In all the vastness of space, in all the billions of light years of mostly nothing, there's this tiny planet where atoms have arranged themselves into beings who can love and laugh and create and dream and wonder. That's not depressing. That's miraculous. So yes, Earth is small. Earth is smaller than nothing, but you exist on it. You're aware of it. You can contemplate your own smallness and find meaning in the contemplation. And that makes all the difference. Good night. Sleep well on this tiny, precious planet. There's nowhere else quite like it. And the next time you feel insignificant, remember, you are the universe's way of knowing itself. You're small, yes, but you're the cosmos becoming aware of the cosmos. And that's something no amount of vastness or emptiness can diminish.